Now we're going to shift our focus away from describing and explaining a cohort into prediction. And when we think of prediction, we think about using data that we have observed to make statements beyond the observed data, outside of the sample you collected. So you know something about a population or a cohort here, but you want to say something about somebody who you have no idea if they're a case or not yet. So you want to predict something about this individual. While the overall goal may be that you want to create an intervention to increase health, an intervention requires causal understanding of the exposure and disease relationship. But what's interesting is that you don't really need to understand the causal relationship to decide who gets an intervention, or who requires an intervention, or who is in need of an intervention. So knowing the cause of the disease may be useful, but it's not really a requirement for prediction. So one case you could think about is being accepted to university doesn't necessarily make an individual drink more. However, if you were going to conduct a public health intervention to reduce risky drinking in a population, then university students is not a bad place to start, because we know that risky drinking is highly prevalent in university students. That doesn't mean that our intervention is going to work by removing people from university. That's not how we're going to reduce risky drinking. So we're not saying that that's a causal relationship, but it's still useful information to predict. Okay. So we can think of prediction as 4 different tasks in epidemiology. You have screening, where you're trying to predict which individuals are more or less likely to have or in the future contract the disease. And usually this is among in an asymptomatic population. Diagnostic testing, where we try to determine or predict whether an individual reporting symptoms has a disease or not in the present moment. So I think in the English language, sometimes we attach a time period that needs to elapse when we think about prediction, as in prediction is something in the future, that we're predicting something that will happen in the future. That's not really the case. So prediction is also used to understand something here and now that we do not know something about. So in this case, you're trying to determine if an individual who has symptoms has a disease or not, here and now. We have prognostic testing. So you're trying to predict something about the future course or outcome of the disease among individuals known to have the disease. And then something that is growing with precision medicine, where we try to characterize which individuals are most likely to benefit from an established intervention. So here are 4 prediction tasks that you might care about and which are important in the epidemiological toolbox. We are going to get familiar with the 2x2 table again. This time we have disease up here as before, where we have y plus, that means that it is a case, y minus, not a case. So an individual has the disease, does not have the disease. On the x-axis, we have a test. So it's not an exposure anymore, now it's a test. The test is either positive or it's negative. If an individual who has the disease has a positive test, we call that a true positive. If an individual has the disease but has a negative test, we call that a false negative. If an individual does not have the disease, has a positive test, that's a false positive. And individuals who do not have the disease and have a negative test, that's a true negative. And there you have the totals out in the margins here. So true positives, false negatives, true negatives. And we're going to use these to define 4 different metrics, which help us understand if a test is performing in a specific way or not. I try to avoid saying performing well or a good test because it really depends on the context. These measurements are, some of the measurements are more important in some contexts and some measurements are less important in some contexts. So it's hard to say generally what we're trying to achieve with the test because it will depend on the specific test and the specific disease. Here it goes. Sensitivity. This is the ability of a test to identify true positives. Okay, so the true positives were the ones who have the disease and tested positive. So it's the proportion of those actually positive for the disease, A plus C, who are identified as positive, A. A divided by A plus C gives you the sensitivity. If you're used to thinking in probability theory as a conditional probability, you can think of it as the probability that you'll have a positive test given that you already have the disease. The probability that you'll have a positive test given that you have the disease. So here we have a bunch of people, the blue bubble here. They have the disease, and our test is positive for these people here. And this is usually what we call a low sensitivity. The test isn't really capturing all of the people who have the disease. High sensitivity here, we have the blue circle here, which represents all the people who have the disease. And the orange circle here shows the individuals who had a positive test. So this test has quite high sensitivity because it's sort of capturing all of the people with the disease. And then if you have a perfect sensitivity, these completely overlap each other. Okay? So sensitivity, the ability of a test to identify true positives. Then we have specificity. So specificity is the ability of a test to identify true negatives. So true negatives is the ones who do not have the disease and have a negative test. Those are the true negatives. So getting specificity, you get that by taking D divided by B plus D. And just like with sensitivity, you might think about this as a conditional probability. That is, the probability that you'll have a negative test given that you don't have the disease. So low specificity, well, that would mean that you have a bunch of people here who don't have the disease, but the test is only negative for a small part of them. High specificity, you have a bunch of people who don't have the disease, and a lot of them are captured by the test. So a lot of them also have a negative test. And perfect specificity, that's when they completely overlap. Then we have the positive predictive value. It's the probability that you have the disease given that you have tested positive. So it's sort of the flip side. Now it's what's the probability that you actually have the disease given that you have tested positive. So it's the proportion of those testing positive, which is A plus B, who have actually had the disease, A. So it's A divided by A plus B. And as a conditional probability, you can think of it as the probability that you have the disease given that your test is positive. And this is important for patients. They care about this because this has an emotional attachment to it. If your doctor tells you that you have a positive test result, how likely are you to actually have the disease? So you can see why patients care about the positive predictive value. Just like before, but now these are flipped. So now we have a bunch of people here who have a positive test result, but only a small fraction of them actually have the disease. So this is a low PPV, positive predictive value. We just say PPV. Here we have a bunch of people who have a positive test, and quite a few of them also have the disease. So this is a high PPV and perfect PPV when they overlap. The other side of the coin would be the negative predictive value. So that's the probability that you do not have the disease given that you have tested negative. So it's the proportion of those testing negative who actually do not have the disease. D divided by C plus D. As a conditional probability, it's the probability that you don't have the disease given that you tested negative. And again, this has an emotional attachment, and it's important for patients because if your doctor tells you that you have a negative test result, how likely are you to not have the disease? A low NPV would mean that you have a bunch of people that tested negative, but only a small fraction of them didn't have the disease. A high negative predictive value means that you have a bunch of people who tested negative and a lot of them didn't have the disease. And perfect NPV when they overlap. So here are 4 different metrics that we can use to assess how a test is performing: sensitivity, specificity, positive predictive value, and negative predictive value.